Hi everyone, welcome back to our NetPlay seminar. Today we are joined by Louis Bouchery, who is currently a postdoctoral researcher at the Technical University of Denmark and at the Copenhagen Center for Social Data Science. During the first half of the seminar, he will introduce us to the art of using machine learning to study human behavior and social systems through the lens of complexity science, with an emphasis on human mobility, as we will see. And during the second half, we will be discussing the use of AI code assistance in research. Without further ado, Luis, the floor is yours.
Thank you. Thank you very much. So I'll talk about human mobility and geography and how they interact. And most of what I will talk about is published in this paper, but there would also be things that are not published yet. And I'll put the link in the chat to the preprint. It should also be at the end. And so as you can see, this is a map of France. And like you can recognize the shape of France. And if we look towards the south of France, you can recognize the mountains and the French Riviera. If we go all the way to the west, you can see a river that goes through the land, and you can see the rugged coast of Brittany. And all of the things I've mentioned so far, you would call them geographical features, right? But the thing is that this map is not a map of the mountains, it's not a map of the borders of France, and it's not a map of the river. It's basically just a scatter plot where every dot is an address. So there's like 30 million addresses in France. And what I want to argue is that basically just looking at all of these addresses able us to capture a lot of geographical features, and this at many scale. So if we zoom now on the city, so this is Paris, we find a new kind of geographical feature, which is a street network. And we also can see a river, and we can see parks, etc. And then we can zoom in even further so that I can show you that I was not lying and that it's really a scatter plot with just dots where every dot is an address. And another point I want to make with all of these is that when you look at human mobility, the space on which people can move is actually constrained. So it's not the whole space that is available. It is a space where addresses are registered. Let be like addresses for where people live, but also workplace, universities, cafes, restaurants, etc. And so when we model human mobility and human behavior, we should somehow take that into account, that not the whole space is available. And so now to get into something more concrete, we're going to study first residential mobility. So when people move from one address to the other, and we're going to do this with data from Denmark. So we have every residential move in Denmark since 1986, and it's approximately 40 million moves between addresses. And on top of that, we have the precise location data of where these houses are. So actually we have coordinates of the doorsteps with a plus minus 2 meter precision, which is actually relevant for the paper that that's precise. And so a common thing in mobility is to study whether or not the distance distribution is a power law, sorry. And so what you have in orange is the distance distributions of all of the moves, so all of the residential moves in Denmark. And what you can see we can plot this in a log plot, and we get this line, which is not so straight. So it's not really a power law. It has different regimes, and there's a bit of fluctuation. And you could argue that there are noise, but in the meantime, there's 40 million points. So there's not so much noise in the data left. And so one of the main hypotheses of the presentation is that this line in orange is the product of two things. So the mobility is the product of two things. So what we have in orange is the observe, this like the probability of observing an event. So the probability of someone moving of this distance r, it's the product of the geography. So the product that there is an opportunity of moving a distance r, or if you prefer that there is two houses that are separated by a distance r, times the probability that people makes the choice of moving. So that they realize the opportunity, and then we get the observe event. And so we already computed the orange line, and now we want to compute the blue line. And it's just computing the pairwise distance distribution between addresses in Denmark. So how we do that is like, for instance, we take the map of Denmark, we plot all of the addresses, we take a point, And then we're going to make a circle and grow, like the circle grow and count all of the addresses that are within the circle. So we do this here, we do this here, etc., etc. And if we do this, we're going to get all of the pairwise distance distribution of addresses in Denmark. And so distribution is going to be this blue line. And so now we have these two distributions. It's great. And then one more thing to say is that if people were to move at random, so when you want to change addresses, instead of like choosing, you would just like the government will like select from a list and say you have to move here. The moving distance distribution would look like the blue one because it's just like random pairs. And so the difference between the orange line and the blue line is actually reflecting the choice people make. And so we had this equation, and so we have the orange part, we have the blue part. So if we are interested in the choice that people make, we can just need to shuffle things around. And so the choice people make should just be the orange part divided by the blue part. So let's do that. Let's divide the orange line by the blue line, and we get the following. So we get a straight line, and this is remarkable for three reasons. The first one, as you can see, the line is very straight. Second of all, it's straight over 5 orders of magnitude. So the kind of power law it exhibits is true from 10 meters all the way to 1 million meter or 1,000 kilometer. And then the last point that is remarkable is the exponent. So if we do a maximum likelihood fit on this power law, we get an exponent of 1 or -1, which basically means that is 1 over the distance. So the cost of when people want to move evolves as 1 over the distance. So as I said, like the blue line could be interpreted as the random case or like a null model case. And what we observe is that the difference between this null model and the reality is 1 over the distance. So that's great, but this is only for Denmark and only for residential mobility, which is quite a specific case. So then we try to extend this to different geographies. So as you've seen in the introduction, we also had data for France. So same legend as before. The blue line is the pairwise distance distribution or the geography. And then the orange line is the moving distance distribution. So here in the case of France, the orange line is truncated on the lower distance because we only had data for move between cities. So it's truncated by distance that corresponds to the size of the city. But the important point is that when we looked at the plot below at the intrinsic distance cost, we get a straight line again with an exponent close to 1. This time is a bit higher. But still, this is another geography, but it's still residential mobility, which is not the most modern way of studying mobility. So what about other types of mobility? So for that, we looked at day-to-day mobility between point of interest. So it's just people geolocated with their phone. And we look at that in San Francisco, Houston, and Singapore. And same thing in orange, it's the moving distance distribution. And in blue, the pairwise distance distribution. And then we do the ratio of the two. And what we obtain is that we also have a straight line with an exponent this time that is still close to 1, but a bit lower. So that's great. And we can say that, okay, we have these things that look somehow universal. But then an interesting thing to look at is if you look at all of these blue lines that are the pair distribution function, you can see that they kind of all have the same shape. There's a bit of fluctuation at the beginning, then it's like a straight line that has the same exponent, and then it decreases as we reach the limit of the system we are studying. And so now we're going to try to spend a tiny bit of time explaining the structure of the pairwise distance function. So it's still the same thing for them. So the line that was blue is no teal, but it's the same thing only for Denmark. And I'll go super quick through that, but there's much more details in the paper. So basically here we can find 3 regimes. The first one is what we call the neighborhood regime. So it's like below 100 meter. And what happens there is that, oh, what is happening? Okay, it's fine. So we have, we model addresses as particle and we put them inside a potential, and then we have a attraction repulsion. So basically what the attraction repulsion means is that basically you want your neighbors to be not so far from you because then you can share cost on electricity, water, etc. But in the meantime, you don't want them too close because you want a house to have a certain size. So there's like a repulsion at small scales. And when you do that from the model, you can get a value from the pairwise distance distribution of cities. And if the plot was working correctly, you would see a fit, but it's not there. But it's okay because I have this slide, which is many cities in Denmark. And what you have in gray is the empirical distribution. And what you have in black is the fit of the model. And the only parameter is actually the radius of the city. And so I hope what you get from this is that we have a pretty good fit of the model on the empirical data for modeling the pairwise distance distribution of a city, so the local one. Then another scale that is interesting is the large scale, so the macro scale. So here it's the scale that kind of corresponds as the distance between cities. And so here what we do is that basically we remark that the position of cities is uniformly random in the space. It just has to be on land, right? And another thing is that cities are not overlapping, because if cities overlap, they are just going to merge. So just going quickly, in orange, you have the ideal gas, so cities that are uniformly distributed on the space. Then in purple, it's the model of hard disk, so cities that cannot overlap. And then in green is the empirical data. So you have this thing at the beginning of the plot where there is no cities compared to the uniform case. But then when you arrive around 10 kilometers, even before, it fits the uniformly random model. And then finally, on the pairwise distance distribution, we have this regime where its slope is equal to 0.67 or around 2/3. And this we can reproduce it with a fractal model of cities. So if you look at the three pictures below, the one in the middle that is highlighted, it's a city in Denmark, and you can see that this kind of exhibits a fractal structure. But there is more on that on the paper. I will just skip it for the talk. And so now we can come back on our mobility and intrinsic distance power law. So one thing is that the exponent was always 1 or -1. And if you are familiar with human mobility, this might remind you of the gravity model or the gravity law that says the probability from moving from city I to city 1 to city 2 is the product of the population divided by the distance. And so if you are quick, you can realize that this product of population is very close to a pairwise distance distribution. And then it's kind of the same thing. The only difference is that the gravity model requires administrative units. So it's like a discrete model, whereas what we did is continuous and just require addresses and extend the gravity model to small distances. But we can also see that it's a bit more than just the gravity law. So now what we are going to do is that instead of looking at what's happening on the whole country, we're going to look at what's happening city by cities. So we're going to first take a small city and a large city, and we plot the same thing, the moving distance distribution and the pairwise distance in orange and blue. And we do the ratio of the two to try to look at the intrinsic distance costs. And so now what happened is that we don't get the straight line anymore. We get a piecewise process or a two-step power law with a small slope first and then a big slope for large distance. And then in pink, it's where the transition between these two slopes happen. And if you look carefully, you can see that this transition happens as at a greater distance for the large city than in the small city. And it hints that this transition distance is somehow related to the radius of a city. And so here I show it for 2 cities, but actually we can see that it happens for many cities in Denmark. It's not all of them, but I hope you can trust that then it's the case for all of them where we have this piecewise process. So rather than looking at all of this plot, what we can look at is the distribution of the 2 exponents of the slope. So here the color match. So what you have in low teal is the exponent of the first part of the piecewise process. So from moves that are actually within the city, so from 10 meters to a few kilometers, and it's around 0.6. And then in the darker shade of teal, you have the exponent for moves that are between cities, so after the pink line, and here you have an exponent of 2. And you can see that the distribution are quite centered and don't overlap. And then the last plot, which is called city size in pink, correspond to the distribution of this transition. And we can see if we fit a log normal distribution or a power law distribution that the distribution is between these two, which correspond to the usual distribution people look at when they look at city size. So that's great. We show that we have kind of a universal behavior at the scales of cities that is different from the gravity model. But this raises a new question, which is how do we go from this local piecewise process to this global straight line that we had before? Because it's the same data. It's just that we looked at it city by city. And it's not clear that the aggregation of the piecewise process should lead to this straight line. And so this is what we are going to try to recover now. So if we look at the intrinsic distance cost, we have the local one that we just saw with 2 colors. So we have an exponent for low distance in the light color and an exponent for the other distance in the darker shade. And then we have the global one, which is just 1 over the distance. We also know that we can express this 2 choice as the ratio between the moving and the pairwise distance distribution, the local one and the global one. And then we also know that these quantities, so the moving and the pairwise distance distribution, the global and the local one are just the mean of the others. And so now with all of the equation we have, we can express the global intrinsic distance cost, so the straight line, with using the local ones. So we express it as a ratio, then we developed the moving term, and then we can replace again the moving term by the local equation. And so what was the goal of doing this was to get this expression where we can express the intrinsic distance cost globally as a function of the local one and the geography. And everything we've done so far was to be able to explain all of the terms in this equation. So we saw that we have a good model for local geography. We also had a good model for global geography. And so basically, if we take this equation, we can express the small pi as what happens at the local case and then the global case. And then we can express the local intrinsic distance cost with a model of the 0.6 and -2 slope. And then we need to decide for the weights. We're just going to take the empirical data, so it corresponds to the number of addresses in each cities. And then the global pair distribution function, the P in blue, is just the sum of the local ones. And so when we do this, we have a new plot appearing in the lower right corner, where here it's like the model. And basically what happened here is that you can see that the tiny dots in black are forming a straight line, which is 1 over the distance. And the colors in the background correspond to the regime. So the light teal is when we are always within a city. The pink part corresponds to the scale of city. So the smallest city is 100 meters and the biggest city is 30 kilometers. And then we have the intra-city distance. And that's kind of the end of the talk. So this is kind of a picture that sum up the main results with the intrinsic distance cost and the local picture that we can recover with our model. And thank you for the attention. And you even have a QR code of the preprint. Thanks. I guess I should keep
Thanks
this.
so much. Thanks so much, Louis. Yeah, I'm sure that there will be many people interested in reading your work. Do we have any questions? I have questions. So if you have any questions, please raise your hand. Go ahead. I think that Jessa
Yeah.
just opened the mic. So start, Jessa, please.
Yeah, so thank you for your talk. I'm really very much interested in what you're doing. But my question is mostly 2 parts. What can you learn that from like this kind of data that you cannot learn from the, I don't know, OpenStreetMap like data set that you can get like online, or maybe like the data set that you can get from the satellites? What is like in the mobility that it gives you like superior results comparing to like the data set that is already there, like to understand like the geography of the cities and the streets and how people like are moving.
Yeah. So maybe one thing. I mean, it's a bit of a shame because it's the slide that got all black. Oh, yeah, why is this doing this? But basically, if you compare it to OpenStreetMap,
Yeah.
OpenStreetMap, you would not get an as good resolution. So I said in the introduction, we get plus minus 2 meters. It's
Mhm.
actually even better than that. So how they got the data is that they looked at the cadastral map of cities. So it's like super precise because it's what people use to build a house and like dispute which part of the land is theirs. And so this enable us to see the fluctuation here
Mhm.
at low distances, where also it's justify all of the model in terms of attraction and repulsion interaction.
Mhm.
Um, I know it's not fully answering your question because it still remains very technical and physicsy argument. But then the second part was you were saying what can it helps in terms of mobility, or
In terms of
can you?
like understanding a geography of a city, because you still have like the point of interest. Like I think your answer was like quite good,
Okay.
like in terms of that. Just to just like point out another part, you just say like big towns are different from like the small towns. Maybe something that is different in big towns is like it's the inequality of the access to certain parts. For example, if it's like, I don't know, like a place that is like only very like, I don't know, very rich people, they can go there. It's just like people that they are living in certain like rich areas, they can go. Like just if you look like in the incoming flux of a certain point of interest, maybe that kind of like differences can show you, because in a small city you don't
Yep.
have like that much of like a diversity in terms of the incoming flux.
Yes. So you completely nailed down basically the follow-up paper on this paper,
Okay.
which is to look at the demographic. Um, Yeah. One thing I could say is like if we look at commuting, for instance, so we have data on where people work and where they live, so we can look how far they live from their workplace. You have this thing in large city that sometimes people can live very close to their workplace, which is not the case at all for most of the other places. And this is in some way huge inequality that large city enable you. So like people that live less than 100 meter from their workplace only exist in big cities.
Okay.
And then kind of more general answer in how to include this framework with a study of inequalities is that basically the all like 1/r thing is kind of an aggregated neural model. And
Mhm.
then you could look at deviation from this for different demographic.
Okay. Thank you so much for your answer.
Nice. So we have another question by Sagar. Please, Sagar, go ahead.
Hi, great talk, Louis.
Thank you, Sagar.
Let me turn my camera on. So I had two questions. The first is, I'm wondering in this in the last question for the large cities, does this capture the sort of, anecdotally, it feels like there's a sort of fragmentation almost that happens in very large cities where, I'm thinking specifically about London or Berlin or New York or something where it's like, you know, if you're in central London, you're in central London and that's its own city. But then also, if you go out like Islington or something, that's a small city in and of itself, even though it's part of a bigger, same in anywhere else, you're in Brooklyn, certain neighborhoods are their own cities. So I'm wondering, one, if this captures that. Um, and the second question I was asking is if you could just spend like a minute talking about sort of what kind of assumptions are made when you treat city side, or when you treat this as an ideal gas? Like, what do what do you think that sort of smooths over?
Yes. Okay, great. So I'll answer to the first question I answer to both, but I'll start with the first. Um, so on this one, where you have all of the cities, if you look you can see my mouse, I hope. If you look at this one,
Yeah, yeah, yeah.
Olsted,
Holstead, yeah.
yeah. So you see that it deviates from the model drastically.
Hmm.
And the reason why it deviates from the model is actually quite interesting. It's basically they built a railway south of the town. And so a new city developed around the train station. And so this is two cities actually, but administratively, it's only one city.
Mm.
And so this it's kind of what you were saying, that if you have a city within the city, and there's like a clear, if there's a park or if there's like fields around it, you should see a deviation such as this one. So this one is quite dramatic, but you can see that if you look carefully, there's a lot of others that have a tiny bit of that. And I think they correspond to actually a city that is two city or something like that. And I
Very
have to say,
interesting.
if you separate the two cities here and refit the model to each of them, it works.
Huh.
So yeah. And then the second part was on the ideal gas here. But it's just basically you take the shape of Denmark and you put points uniformly at random, which is what an ideal gas is.
Mhm.
And because it's an ideal gas, you don't care that the particles are the size, which is what you don't do in the hard disk model. Does it answer the question, or should I be more precise?
No, that makes a lot of sense. Thanks.
Okay. So you can see the orange dot, they all overlap.
Hmm. Yeah, that's kind of what I was wondering. Okay, very nice.
Nice. So I think we will have time maybe for only one additional question. Is there anyone in the room willing to make a question, or can I close? Okay, then I will be the volunteer. So, as I understood in your framework, you are so far have used Euclidean distances, and Euclidean distances are perfect if you are talking about maps, right? Because it makes totally sense measure Euclidean distance between 2 points in like a flat space. But we live in a three-dimensional world, and of course, if I want to estimate the distance that will take me to go from point A to point B, maybe I should take another parameters, such as, for example, travel time, how many transfers should I make to reach there, what's the elevation of the place. So have you tested the framework with this kind of network travel time or generalized cost? And if you have done so, how sensitive are the inferred power laws to this class of anisotropies, which of course will be in terms of cities, places like coastlines, like bridges, transit topology. How sensitive would be these inferred power laws to these more real city architectures?
I mean, it's yeah. So we didn't do it, but I would still say that it's still the real data. So it's in the data. Many points. The first thing is, in what we're doing, we kind of aggregating everything. So it removed this effect a bit because we looked at in all direction all of the time and all points. So because we're not looking at individual from A to B things, we have this problem less. Then another thing on it is that this distribution, like this spacewise thing in the city, could be due to that. Like, I don't know, because you could argue that as long as you stay within the city, there is a fair ratio of how many meters you want to do and how long it's going to take. But when you go between cities, you might have a highway or a bigger road where you can go much faster or something like that, which makes that the distance are not the Euclidean distance anymore. And that's maybe why we would see this different exponent appearing. And
Nice. Thanks so much.
yeah, that's just one last thing. I know
Yeah,
that
go ahead.
when we look at the commuting, we don't get the clean parallel, we get a piecewise thing. And because you could argue that when you change addresses, you actually don't really care of the travel time between the two addresses. It's more about how far they are and a lot of other things. But when you look for your work, you would care about this. So maybe it could explain this piecewise things, but I'm not sure. Thanks.
Nice, nice. Thanks so much, Louis. I hope that we can keep the discussion in other place. It's very, very interesting research. So there is kind of a remaining meeting time, and we are still not sure why this is going on, but it seems that in less than 3 minutes, basically this meeting will finish. So we propose to restart the meeting, of course, without the recording, because of what you told us at the beginning. And then we can proceed with the second part. Is that okay?